Good afternoon, everyone. This is Daniel Dibaba. I'm a PhD in epidemiology from Tennessee Clinical and Translational Science Institute. Today, we will discuss about data management, preparing your data for analysis. Can you all hear me?
Yes.
Yes.
Thank you. So at the end of this presentation, you will be able to describe data management, understand data management best practices, describe correct variable naming rules, understand data consistency and validation. We'll also discuss about metadata that are important to accompany data when you transfer for analysis. And we also describe data storage requirements. So data management is described as the practice of collecting, cleaning, validating, and securely storing and preparing your data for analysis and using data. So data management begins at the point of collecting the data. If the data collection instruments are not valid, then the data may not be valid either. So data is collected either using questionnaire, as we'll see in the next slide. And if the data collection instruments such as questionnaire, surveys, and the likes are not valid, and then the data that's collected would not be valid either. And that means the analysis that depends on the data would not be valid either. So data collection method should generate as many data as possible. When we conduct data analysis, we usually adjust for potential confounding variables. That means when we look at the association between a given variable and an outcome variable, or a prognosis of a patient, we also want to make sure that the association is not actually due to unaccounted variables or variables that are not the exposure and outcome variable. If certain variables are the cause for the association, that would result in a misleading conclusion from studies. So what we usually do is either at the design of the study or when the analysis is conducted, we take care of the impacts of certain kind of variables or confounding variables. For that purpose, when data are collected, it's wise that the data collection methods generate as many data as possible. So this is what the data cycle looks like. Data is collected from subjects. Could also be about devices, but mostly about human subjects. Could also be about animals. And then data are collected using different software such as RedCap, and then the data are validated for accuracy. We'll look at when we look at about the data values, what we mean by validation. And then data are transferred for storage in the cloud or in designated data storage facilities. At the University of Tennessee, OneDrive is one way to store the data. We'll discuss about that as well. And the data are stored and from the storage cloud or whatever that is. It could also be office computer. The data is transferred for analysis. The data are cleaned for the analysis, and finally the analysis are conducted and the results are reported back to those who are interested or to the public. So this is what the data cycle looks like. It's very important to know what is important at each stage of the data cycle. So data and data management, we start with the data collection. In medical research, data are collected using interviews, questionnaires, and surveys. Surveys are shorter forms of questionnaire. Data are also collected using observation, and data are collected during routine medical history and physical examinations or clicking on patients. And data are also extracted from electronic health record. Data are collected from biologic material samples, like such as specimens. Data are collected during imaging. At the University of Tennessee, as I mentioned, RedCap is a software that's usually used for collection of data. Question Pro and Qualtrics are other data collection softwares that are approved by the University of Tennessee. So data collection instruments should be tested, they should be validated and tailored for the research purposes. Sometimes multiple questions might be about the same topic, and we want to make sure that there is consistency in the questionnaires that are related to about certain item. So we use sometimes we conduct kind of pilots data collection and validate the questionnaires are valid and will measure the property that we are trying to measure. Um, so data like questionnaire validation or data collection instrument validation is one important aspect when we discuss about data management. Questionnaires and surveys are tested for internal consistency using Chromebox Alpha or other consistency measures. Using pilot studies, the ability of study instrument who measure the features they are supposed to measure is evaluated. Sometimes data collection instrument or methods are tested against gold standard methods. For a study to be valid, the data collection method should also be valid. Otherwise, would we junk in, junk out? Like if we don't focus on validating the questionnaires and the data that are collected are not the right data, or if there are a lot of measurement errors, and then the study that would depend on data that comes from invalidated or invalid questionnaires, invalid data collection instruments would also be invalid. The other important aspect of data management is about variables, especially people who conduct data analysis usually almost always deal with variables. So variables are features or data items that vary from a person to a person or from one study unit to another. Examples of variables are systolic blood pressure, total cholesterol, age, gender, BMI or body mass index, temperature, treatment type. So for example, if we take cholesterol in inpatient or outpatient department, whenever we receive patients, if you are interested in their blood cholesterol, when we measure a blood cholesterol of one patient, it's likely to vary from that of the other patient. That's why we use the word variable to name this kind of data. So the variable substitute, it's a code that substitutes all the cholesterol and or all the age values that are collected from the participant. So there are certain rules of how to name variable names. This vary these are they are different based on the statistical analysis softwares that are used for the analysis, but there are some certain general rules we have to always stick to. So variable names should start with alphabet, but in SAS statistical analysis software as well as R, they can also start with, for example, in SAS, variables can start with underscore, the underscore symbol. In R, variable can also start with a period. In both SAS and R, underscore can appear anywhere after the first position. Um, I don't think it's a good um, it's a good habit to start variable names with underscore or period unless there are any some requirement for that. It's always better to start variable names with alphabets. And in R, periods can also be used in variable names. And variable names can have numbers, but the number should appear anywhere after the first position. Numbers cannot appear at the beginning of a variable name. So, for example, let's say the variable name is age. We cannot put one age, or maybe want to indicate the age is collected in 2020. We can't say 20 age. We can say age 20. The numbers can appear on the right side after the first position, but they cannot appear in the first position in variable names. It's a good practice to form the variable names from two or less words. When the analysis is conducted in SAS, it's and also in R as well. It's possible to add labels to variable names, so we can use like the dictionary that follows the data. But it's always a good practice to name variable names from short words. SAS converts spaces in variable names to underscore. R often converts spaces to period in earlier versions, but right now R keeps spaces in newer R versions. That means if, for example, in the original Excel data or the data that was shared with the biostatisticians, if the age variable is age, for example, age in months, R can keep the space right now. So, but when you use in R, you have to either use the backward facing single quotation mark that's usually found on the left, like under the tilde or the escape on the keyboard, or you have to put it in a quotation mark. SAS is not a case sensitive. Both age and capital age that starts by capital A and age that started with a small a refer to the same variable in SAS, but R is case sensitive. That means the variable that starts with a capital A and that starts with a small letter A, both are they are different in R, but they are the same in SAS. So we have to make sure we have unique variable names in dataset, especially if the analysis would not be conducted in R. But it's usually a good practice to keep unique variable names. So we can keep the same variable, only different in cases, especially when the analysis has to be conducted using R. So the variable name should be as short as possible. Some software truncate names longer than certain lengths. For example, SAS allows up to 32 characters for variable names. SAS also reserves some name that start and end with an underscore for variables automatically generated. For example, Underscore and underscore stands for number. For example, if you want to create a list in your data, beginning from 1 to up to the end of your data, you can use underscore and underscore. Error, underscore error, underscore, and underscore in file, underscore, all these are reserved for variables that are automatically generated by SAS. So we try to avoid using this in variable names. If you have any question, you can stop me in the middle. I hope all of you can unmute yourself and you can speak up and I will stop and address your question. So the other important aspect of data management is about values. The values are the different possible data a variable can have. So for example, age has numeric values ranging from 0 and above. Um, and sex is either male or biological sex is either male or female. The values of a categorical variables can be coded. For example, sex can have a value of 0 and 1. It can also have M and F, or male and female, but we have to be consistent in which one we use. So what the codes represent must be provided in data dictionary. We'll discuss about the metadata around the end of our discussion. Consistency is always important in representing the values of a variable. For example, if we use M and F for values of X, we must not mix with male and female or with 0 and 1. And we have to be consistently using M or F throughout. So this is an example of incorrect data values. For example, in this table under age, we have age values without specifying whether it is in years or in months. It's a good idea it's a good practice to convert all the values into the same units. So if we want age to be in years, we have to convert the variables, the values in months, we have to divide it by 12 and convert it to years. If we want it in months, we have to just multiply by 12. But it's very good practice to convert into the same units in your data. And we have to describe what the units are in the data dictionary, and we don't have to include the units in along with the values. Sorry, along with the values. So under gender, so there is inconsistency. We started with numeric codes 0 and 1, and then we used M and F, and then we also use male. There is a lot of inconsistency. We have to be consistent in using. So we have to either stick to 0 and 1, or use F and M throughout, or use male and female. We have to be consistent. Under the BMI, there are a BMI of 200, which is unlikely. It's very high. So unless otherwise the data is coming from like an outlier, we have to make sure the data are correctly entered, and we have to validate that. We have to check again. There could be some errors in derivation of the data. There could be some error in data measurement. So whenever we suspect a data is an outlier and it's not valid, we have to go back and see the source and make sure that the data are correctly entered and there are no measurement errors. In case of under the fasting blood glucose, we have numeric data and character data mixed, and this will create some problems when the data analysis is conducted. So we have to be consistently use the numeric data. in such cases. So missing values are other important attributes that's all, usually problematic when data are collected and when we conduct data analysis. So during data collection, participants may intentionally skip some questions or refuse to provide them. Laboratory data may also become undetectable and may be left empty, and this might lead to missing data. So we should attempt to get and fill the missing data from original sources before we transfer the data and store them. Missing data that cannot be retrieved by the investigators may be replaced during analysis using data imputation methods. But the best practice is if we can replace the data, if we can get back and contact the subject, the study participant, and get the data and replace the missing values, that's a better practice. But if that doesn't happen, and if the number of missing values would impact the study power, and then the good practice is we have to conduct some imputation methods to replace the data. For continuous variables, um, we might use based on the data distribution. We might replace the missing values by the average value or the mean value. We might also replace them by the median, or we might replace by numbers closest to the data points that are missing, or by the mode or the most frequent data. Participants with large number of missing data may also be excluded from analysis. Whenever participants are excluded from the study or from the analysis, we should compare them to those included for basic characteristics and report the finding. So we have to compare the study participants that are excluded from analysis to the participants who have been included in the analysis for certain baseline characteristics or attributes. If there are very significant differences, there can be certain reasons for the missingness of the data, or that means the data is not missing at random. We have to make sure there is no such kind of like informatic kind of missing. So data storage is an important aspect of data management. So when data are collected, validated, and cleaned, and secure, and they are securely stored for continuous use and replication of the study. Funders usually require varied lengths of data retention. The most common length of retention is about three years after the completion of the study or the final special report to NIH for NIH-funded studies. According to NIH, federal institutions must retain records for 3 years from the date of the submission of the annual federal financial report to NIH. Records of research conducted under the U.S. Food and Drug Administration investigational new drug 2021 CFR 312 and 62C must be retained for about 2 years. So data retention periods varies from institution to institution, and also varies based on whether the data is funded or not. But it's a good practice to store data as long as possible. Most longitudinal studies and other large studies, they keep the data for decades and decades. And whenever studies originate from such research studies, you can go back and replicate the study. You can conduct the analysis and confirm the analysis have been correctly conducted. Sometimes um, the readers might question whether there is any problem in the conduct of the research. They might want to retrieve the data and replicate your study or in any of the researchers' study that use the data. So in such cases, they would go back and request for the data. If there is no data, that will result in probably reduction of the published manuscript. So we don't want that to happen. So we have to always make sure that we have the data stored and as long as possible. But there are specific requirements. For example, as mentioned here, NIH requires about 3 years of data retention. So make sure that you identify what is the required length of or duration of data retention at your department or the institution, or if a funding is involved from the funder. So clinical research records are stored in a manner that ensures privacy. That means the data would not be accessed by and unnecessarily accessed by every person. Confidentiality, it's both a similar term, and security and accessibility. When we talk about confidentiality, that means um, even though the participants have allowed their data to be used for research purposes, they have not allowed every person to have access to their personal information. So we have to make sure that when we store data, the data we adhere to rules of privacy and confidentiality. We have to make sure that we don't include, especially like when we transfer data, we have to make sure that we don't include the name of the participant, the address of the participant, contact information such as email, phone number, and we don't include other identifying information such as the birth date and the likes. We have to de-identify data when we share with biostatisticians or research personnel, or when we collaborate with other researchers. We have to make sure we don't include a patient's personal information. We have to de-identify the data. What that means, we have to remove all protected health information such as age, such as name, address, contact information, date of birth, social security number, and sometimes hospital ID number and the likes. So in terms of security, we'll discuss about this in more detail. So records can be kept in hard copy, in electronic or other media form. The security of the data must be ensured by storing on encrypted designated computers protected by username and password. So this is very important. We can't store data that are generated and used at the University of Tennessee on your personal computer, because our personal computers are more at risk of security breach. So we don't want to store research data on our personal computers. We have to make sure we store the data on university property or designated highly secure office computers that are username and password protected and encrypted. At the University of Tennessee, data can be stored on password protected office computers and permitted clouds such as the OneDrive. It varies from institution to institution. Some universities also allow Dropbox, but at the University of Tennessee, for now, as long as I know, it's only OneDrive right now that's allowed. There was also the SharePoint. I think it's no longer being used at the University of Tennessee. So stored data must be accessible for continuous use. Like I said, 5 years, maybe 7 years after you conducted your study, or published a manuscript, an inquisitive researcher might want to say, I want to look at your data, I want to replicate your study. You have to make sure that you are keeping your data. There are situations where there is an nutrition researcher who was very famous, like Dr. Oz, but he's not Dr. Oz. He's from, I think, from Cornell University. He published a lot of manuscripts in high impact journals, but at some point, people started questioning his research and they want to go back and conduct the analysis, but the data were no longer accessible. And so his research had to be redacted, which causes his reputation and his career. Um, so it's a very good practice to keep and store the data securely for as long as possible. The stored data must have accompanying metadata or information that help in the interpretation of the data. I will discuss in detail about metadata in the next slides. So data transfer at the University of Tennessee, data are transferred using the vault, a courier at this link, the vault.utk.edu. So and on this page, you can send a very large data set without having to compress it. And data, sometimes bigger data like 20 gigabyte or something cannot be transferred using the regular email. And it's not the safest way to send data. So at the University of Tennessee, we use the vault.utk.edu. The data transferred using the vault stays for about 20 days. So it has to be downloaded before it expires. It expires within about 3 weeks. So data can also be shared with team members using the Microsoft's OneDrive at this link. Whenever data are shared, it's important that the data are not divided into different spreadsheets or sheets based on the exposure or a group. This is very important because when you share data that is likely to be combined for the analysis, it sometimes happens that there is a formatting issue. Even though the variable names in both sheets or multiple sheets are the same, sometimes some variable are saved as numeric, while in another sheet they are stored as categorical or as character variable, or the decimal point is one can be numeric and integer, while another would be double and has decimal point, something like that. When you try to combine those kind of data in softwares, it consumes a lot of time if you have to convert so many variables like that. So whenever data are shared, it's very important that um, they are first combined before they are shared. It's just copy and paste if the variable names are the same. So group can also be included as a variable instead. So we'll see that in next slide. So for example, this is a random data that I generated. So you will see a lot of repeated numbers. Just let's take as an example. So for example, we have data that's sheet that's named ACE or angiotensin converting enzyme, and no ACE. So most of the time, this is the way investigators share their data for analysis. The best way would be to combine this data. So we have uh, Here we have the variable age, sex, systolic blood pressure, diastolic blood pressure, and the ACE. So in ACE, we cannot click this one right now, but in ACE, we have ID, age, sex, systolic blood pressure, and diastolic blood pressure. We don't have ACE. In now ACE, we also have ID, age, sex, systolic blood pressure, and diastolic blood pressure. And those data are about half of what we see here. But the good practice is if the variable names like here are the same, we can combine them and differentiate whether they come from the ACE or no ACE by specifying like here. So otherwise, when we try to like when you send it to data analysis or biostatisticians, they sometimes there are issues about the format, and they have to convert into the same format before they are able to combine them. So rather than sending data with multiple sheets, it would be better to consolidate the sheets and differentiate categories using a variable. In the shown example, rather than having the ACE and now ACE sheet, we can combine the data and use ACE variable to differentiate category. So the next one is metadata. So metadata is the information that accompany data and help with the use and interpretation of the data. Metadata includes the information about the data, when it was collected, who collected the data, and how it was collected, and data dictionary or code book. So metadata is the information that accompanies the data and is helpful for understanding of what the data stand for, but they are not included in the analysis themselves as the data. So data dictionary or core book has information about variables, the description of the variables, the value codes and their definition, and derivation formulas, and so on. So for example, this is an example data dictionary or core book. We have the variables listed here and description of what the variable stands for, the information about the values, and we can also put remarks. We can add any additional information that may help in understanding what the variable stands for. So for example, for age is a continuous variable in a hypothetical data, and the values range from birth to 18 years. The population is a pediatric population. Sex, it's a biological sex. The description is the biological sex, and the possible values are 0, which stands for female, 1, which stands for male. Um, and parents, the description is whether parents live together or not. 0 if they are not living together, 1 if yes. So we can include and we should keep adding all the variables that are included in your data set and make sure that the data dictionary are kept along with the data, like when the data are stored as well. Otherwise, imagine after, say, a couple of years when you go back and see if you only have the spreadsheet for the data and you have only zeros and ones, you never know what zeros stands for and one stands for. If we don't have the description about the variable parents, for example, we never know what parents stands for. So metadata is very important, and it's a good practice to accompany your data with metadata, including data dictionary or code book, when you transfer your data for analysis by biostatisticians or epidemiologists. So regardless, for example, has data dictionary, which is very large. I might we might come back to this and look at what it looks like at the end of our presentation. ERIC is another large study, about 15,000 participants. It also has publicly available data dictionary that helps to understand what the data, what the variables and values stand for. So metadata gives meaning to the data by storing information about the data. For example, without looking at the data dictionary, we cannot tell what the value codes of a variable mean. The relevance of the metadata increases as the data ages and the memories are lost. So in summary, data management is important from it's important in the time data are collected, validated, transferred, stored, and used and reported. So we have to always stick to certain best practices, variable naming rules, values, and validation, data dictionary, a missing value, how to handle the missing value. All those sorts of best practices are very important when we collect data, store data, transfer data, use and report the findings from data analysis. So we should comply with variable naming rules and be consistent in entering data values. It's a good practice to have another eye to look at whether the data entered into databases are accurate. We should attempt to replace missing data with data from original sources. We should validate data for accuracy before using or sharing. Data retention is required for reuse and for replication of study and for data audits. So when we say data audit, a funding agency might randomly say, I would like to look at the data generated from the study that was funded by the institution. So if you don't store the data properly and accompany with metadata, data dictionary, and the likes, there would be a problem if you are not able to describe what each value of your data refers to or what each variable name refers to. So metadata must be stored and shared with data. Another important point when we talk about data management is that data privacy and confidentiality is very important. We have the HIPAA compliance. Um, so we have to make sure that we obey the requirement for data confidentiality. We have to make sure that the data that's shared between collaborators and between the biostatisticians and epidemiologists do not include protected health information. So that's it. Thank you very much for your attendance. We can now discuss if you have any question. You can unmute, everybody can unmute yourself. And if you have any question or suggestion. So thank you very much. This presentation was sponsored by the Tennessee Clinical and Translational Science Institute at the University of Tennessee Health Science Center. Thank you, Jeff. Thank you. So if you have a study and you want the bird clinics, the biostatistics, epidemiology, and research design unit to assist you in study in your and to assist you with the study design or data analysis, you can go to the tnctsi .edu, tnctsi.uthsc.edu, and schedule through the bird clinic. Thank you. Um, yeah, one other thing that I didn't show was, let me see, I can go back. Yeah, let me see if I can show. Yeah, yeah, this is the data dictionary or the metadata following the regarded study. Uh, for example, they have source of data. This is like it's generated using SAS. The ACR is a variable name. Um, this is how it is generated. Urinary albumin divided by creatinine ratio, say milligram per gram. It's calculated, and then we have AFB ECG. We have description about that, and this is about the data that are generated or derived variables. But if we keep going, we have other data, like we also have like code or value description, frequency, percent. We have the diabetes underscore med SR pills. Um, this is how the variable is generated. The code is yes or no. So this is a kind of metadata that from the regarded study. The other one is, let me go back. The Eric. So ERIC stands for Atherosclerosis Risk in Community Study. This data dictionary was published in October 2018. So we have here very organized data dictionary where we have subject ID, center, vCenter, and social demographic factors like this. They are properly described. Yep, so that's what it looks like. You can have a look at it. If you want Eric and regardless data dictionaries, you can search them and look at what they look like and uh, adopt in your research. Thank you.